In this video, I want to talk about conditional statements, also called implications. And these, in some sense, are the bedrock of mathematical statements. We really like these. And they're of the form, if something, then something else. And we call that first something, we call that the condition or the hypothesis. The then something else, we call the conclusion. I might even say just the if part and the then part. A lot of mathematicians just say that, and that's fine. Now, I'll tell you the truth table for it. And again, we write if P then Q in logical symbols using this. This is a nice logical formula for that. So the truth table is as follows. Again, we need values of P and Q. And we're interested in this conditional P implies Q, or if P then Q. So we have true, true, false, false, true, false, true, false. So these are all the possible truth values for P and Q. And then P implies Q. Let's explore this a little bit. Let me come up with an example. So maybe something along the lines of if you get 100% on the midterm, I will give you $1. Okay, so in this example here, the if part, the P, is getting 100% on the midterm. And the then part, which I should put the word then in here actually, then I will give you $1. Sometimes in English we don't use the word then all the time, but it's kind of implied. We'll try and make it as precise as possible in math, so we will say if and then. So there's our then part. We'll call that Q. So let's look at the various truth values, and let's see when I'm lying to you here. And we'll call that false. So am I telling you the truth if P is Q and Q is true? If you get 100% down the midterm, so P is true, and I actually give you $1, am I telling you the truth with this sentence? Am I lying to you? I'm not lying to you. I'm telling the truth. So that is true. Let's look at the second. So in this case, you do get 100% on the midterm, but Q is false, so I don't give you $1. Well, then this sentence here, P implies Q. If you get 100% on the midterm, then I give you $1. I was lying to you, so it is false. These situations here, we have to be a little careful. It says here, if you get 100% on the midterm. So in these situations, you don't get 100% on the midterm. So this sentence doesn't really apply to you. So there's no way you can tell I'm lying just from this information here. So we call these situations vacuously true. If the if part is false, then the conditional kind of doesn't apply. So we call these situations vacuously true. But they're true nonetheless. The best way to think about the truth table for an if-then statement is it's only false when the if part is true and the then part is false. I like to call this the dreaded row, and you'll see why once we get into proofs a little more. We want to avoid situations where the dreaded row occur. If we can show that the dreaded row never occurs, then all that's left is the possibility of our if-then statement always being true. So that's kind of the idea here. Now, again, there is a bunch of ways of writing if-then statements. If you don't want to say if P then Q, you can say P implies Q. Sometimes you'll see it as Q if P, so some people will write the if part afterwards. You'll see things like P only if Q, you might see that. You might see P is sufficient for Q, which means if you know P is true, then Q must be true. And Q is necessary for P, which means that for any chance that for P to be true, it means that Q must be true. These don't come up as often as if P then Q, but they're good to know. So let's do this example here, example 2.3, which says, express this if-then statement in the other 5 ways above. So we'll express them in these 5 ways just to get some practice doing that. Let's scroll up to give us a little more room. So let's identify our P and our Q, our if part and our then part. Here is our if part. Here is our then part. Okay. So we have if P then Q. So the first way is P implies Q. So we'd write that as, well, the last digit of a number and being even. We're just kind of conjugating our verbs a little bit. So instead of is, it just makes more sense grammatically to say being. So the last digit of a number n being even. Oh, that's the wrong pen. Even implies that n is even. So that's the first way we express it. Exact same meaning as if P then Q. P implies Q. Just another way of writing it. They're logically equivalent. They have the same truth values. Okay, so the next one is n is even. That's Q. Only if the last digit of n is even. And we should say what n is, so maybe here we could say the number. Ooh, that's not what I wanted here. The number. The number n is even, only if the last digit of n is even. Again, all these mean the same. The third is the last digit of a number n is even, only if n is even. The fourth, the last digit of a number n being even, so that's P, is sufficient for n being even. Again, instead of is, we're using being just because it's more grammatically correct. And finally, we're going to do Q is necessary for P. Oh, I didn't want to move that. Q is necessary for P. So let's write that. So a number, or the number, n being even is necessary, Yes, is necessary for the last digit of n being even. Again, all of these statements here mean the exact same thing as if the last digit of a number n is even, then n is even. So they're logically equivalent. They mean the exact same thing logically. The converse of a conditional statement just flips where the if part and the then part are. So let's say if we had P implies Q, the original statement, being, let's say, if, let's say, C is a cat, then C is a mammal. So let's say that's P implies Q. Well, the converse is going to be just flipping the Q and the P. So it becomes Q implies P. That's the converse of P implies Q. And that is, if C is a mammal, then C is a cat. So that's the converse of the original statement above. And just thinking about this, you can see that these statements are not logically equivalent. They do not have the same truth values as the original. That's important. This statement is always true. Cats are mammals. Pick any cat that you like. It's also a mammal. There's never a situation where P is true and Q is false. So something is a cat and something is not a mammal. That just never happens. But you could imagine situations where you have mammals that aren't cats. So maybe a dog, for example. That satisfies the if part, so the if part is true, but then the then part is not. So these are not logically equivalent. And let's just do the truth table of that quickly. So we have P, we have Q, we have Q implies P, so the converse of P implies Q. Again, it's kind of the same idea. But the idea is that, remember, it's false exactly when the if part is true and the then part is false, which is in this row. So it looks a little bit different. So it's only false then and true otherwise. Again, the if part is true and the then part is false. So you can see that these statements are not logically equivalent. We'll get into this in a little more detail very soon. But it's a very important concept, knowing what a converse is. In fact, we are going to use this right now. And there's a very powerful type of statement, which is a biconditional statement. And this means that a conditional statement and its converse are both true. In mathematics, anytime we have these situations, it's a very powerful thing because it eliminates other options. It basically means that P and Q are kind of the same thing in some sense, and we'll get into that in more detail later. But what's going on here, we can kind of figure it out. So again, let's do a truth table. We have P, we have Q, and let's do it all. So we have P implies Q, we have Q implies P, and then we have this P if and only if Q. We write it like this. And remember, this means, this is just a shorthand to mean that P implies Q and Q implies P. So we'll have to use our rules for and here to determine the truth table. Again, let's write down all our situations. True, true, false, false, true, false, true, false. And then P implies Q is false exactly when the if part is true and the then part is false. So that's then. And Q implies P is false exactly when the if part is true, which in this case is Q, and the then part is false. So it's there, and it's true otherwise. Now, P if and only if Q, the biconditional, remember that's P implies Q and Q implies P, so both need to be true. Again, this is just the exact same thing as that, just written a little bit differently. So we look here. P implies Q is true and Q implies P is true when both P and Q are true, so it's true here. It's true when both P and Q are false here. And it's false in the other two situations, when one is true and one is false. So if we know an if and only if sentence is true, we know that either both P and Q are true or both P and Q are false. There's no way that one can be true and one can be false if we know that this is true. And let me give you an example of a statement where let's do one first where the original statement is true but the converse isn't. Then let's modify it to make it something where the biconditional is true. So here's my example. If a counting number, let's say n, ends as the last digit, ends in a 5, then n is divisible by 5. So that's always true. You know that if numbers end in a 5, then they're divisible by 5. 5, 15, 25, 35, whatever. That is always true. But the converse, so this is true, I'll put like a little smiley face there. That's always true. The converse, however, is not. If a counting number n is divisible by 5, then it ends in a 5. That is not true. So here is, let me mark this in, this is P implies Q. This is the converse, Q implies P. So in this situation, this is not true. We can think of a number that's divisible by 5 that doesn't end in a 5. How about 10? And we call these situations where we can find something where the if part is true and the then part is false. We call them counterexamples, which we'll talk about in more detail later. But a counterexample to the second one is n equals 10. That's divisible by 5, but it doesn't end in a 5. Now maybe pause the video and see if you can slightly modify this statement so that both the conditional and the converse are true. Just a slight modification. So pause the video now and give that a go. Okay, so we know that numbers that are divisible by 5, they're like 5, 10, 15, 20, 25, 30, etc. They always end in a 5 or a 0. So now we can modify this so that both the original conditional statement and its converse are true by just changing ends in a 5 to ends in a 5 or 0. So let's go ahead and do that. I'll write that in green here, or 0. And down here, same thing. Then it ends in a 5 or a 0. Now both the original conditional statement and its converse are true. There's no more counterexample. This is kind of a strong statement. It means that all numbers that are divisible by 5 end in a 5 or a 0, and it also means that all numbers that end in a 5 or a 0 are divisible by 5. So those concepts are the same concept in some sense, just reworded or expressed differently. And that's very important in math. When we find situations like that, we love it. Now, again, there are other ways to word biconditionals. These two are kind of the most common, if and only if, and sometimes we just shorten it to if with two F's. Note the two F's if you write that. That means if and only if. I want to revisit example 2.5 in a later video when we get a little more used to the idea of doing proofs. So we'll come back to this one. So don't worry about this just yet. Two more topics I want to talk to you about in this video. The first one is order of operations. So here's our order of operations here. Brackets always come first. You always do the things inside of brackets first. Then anything that's a negative, you apply that. And in logic, we kind of think of and as like a multiplication. And we think of or like an addition. So it's almost the same as bedmass in some sense. You do your brackets, and then your negative, and then your multiplications, then your additions. And then you have these implications. You do your conditional, and then your biconditionals last. To be completely honest, usually mathematicians want to make things as clear as possible. So unless you're doing lots and lots of logic and the order of operations are second nature to you, you can use extra brackets just to indicate what you want to happen first. But just as an example, let's do this one here. So we want to make a truth table. So let's do it as a P and a Q. So we need the truth values for P and Q, and I'll make it kind of big so that we have enough room for everything that we need to write down. And of course, the truth values, we put all possible combinations. All right. So let's go ahead and work out the things in brackets first. So we need to work out this guy and this guy. Okay, so let's start with this guy. We have P or not Q. So we need to apply the not before we apply the or, since it's first in the order of operations. So let's figure out what not Q is. Okay, so not Q, well, that deals with when Q is true or false, so it just changes the truth value. So it becomes false, true, false, true. Okay. Now we already have P, so we can do P or not Q. So that'll be that bit. All right. Let's go ahead. So remember that ors are false exactly when both sides of the or are false. So we need P to be false and not Q to be false in order for this or statement to be false. So let's look at it. P is true, so we know automatically we don't even have to look at the truth value for not Q in the first row. So we know this is true since one of them is true. Same with the second row. That's true as well, since we know P is true in the second row. Okay, so let's look at the third row. P is false, not Q is false. That's the only situation where an OR is false. And finally, we have false and true. P false, not Q true. One of them is true, so this is true. Which means P or not Q is false exactly when P is false and Q is true. Okay, let's keep going. We already have not Q, so we don't need to write it again. And remember, we have ands coming before ors, so we need to figure out not Q and P, and then do and Q. Okay, let's go ahead. So we need not Q and P. And again, this is true exactly when both not Q is true and P is true. And that situation is right here, is in row 2. And you can check that all the other rows don't have that situation, so it's going to be false. Okay? So now, let's do not Q and P, or Q. And again, this is kind of hard to read in some sense if you're not super comfortable with logic. So what you could do to make things a little bit easier, you could just put in some brackets here like that. And that might help you, even though the order of operations says that you don't need to put in brackets there, some superfluous brackets still might make it easier to read. So let's go ahead and do this one. So not Q and P, or Q. So again, only one of them needs to be true in order for the OR to be true. So we look at true, false. So this is true. Oh, let me do this in black. Okay, let's continue. So we have false and true. So true. Then we have true. Well, if that's true, if Q is true, then the OR statement is true. Since here is Q, only one of them needs to be true. And here we have false. False. So our statement here is false exactly when Q is false and not Q and P is false. Okay? So we have those done. So that's great. And maybe to simplify our lives a little bit more, I'm going to just label these expressions. I'm going to call this S, this P or not Q, and I'm going to call this second bracket here, I'm going to call this T, just so I don't have to write a bunch of things here. So, and if I wanted to rewrite this, it would look like S, if and only if Q implies T. Okay. So we have that. We figured out S and T. Now we just have to deal with the remaining conditional and biconditional. So the order of operations says do the conditional first. So let's go ahead. We need Q implies this T. So this here, of course, is our T, and our S was this guy. No, it wasn't. Our S was this guy. Okay. So, let's look at it. So, Q is true here. T is true here. So, true and true is true. I'll do this again in black. Next one, we have the if part is false. Well, if the if part is false, there's no way for the implication to be false. Remember, implications are false exactly when the if part is true and the then part is false. So if we know that the if part is false, we don't need to look anymore. It's vacuously true. Let's look at the next situation. So we have Q is true and T is true. So this is true. And finally, we have the situation where Q is false. Well, if Q is false, again, we don't really care about the truth value of the other side. We have that the if part is false, which means that the implication can't be false. Okay? So this is nice. In fact, we'll talk about this in a little more detail. But if you're in a situation where all the truth values are true, we call this a tautology. It's never false. It's like saying a number is even or odd. Of course, a number is even or odd. Every number is either even or odd, I should say a counting number. That's a tautology. It's just never false. Okay? So we have that. So now we just need S. If and only if this, and I'm going to put this in brackets just to make it a little easier to read, Q implies, T. And remember that our S is this expression here, P or not Q. And I just wrote it as S. I defined the variable S to represent that, just for ease of writing. So let's go ahead and look at that. And remember, biconditionals are true exactly when the truth values of both sides match, and false when they don't match. So let's go ahead and look at it. Here we have true, true. So this is true. Here we have true, true. They match, so that's true. Here we have false, true. They don't match, so this is false. And finally we have true, true. So this is true. And in some sense, and this example here, you can see that kind of adding this tautology on one side of an if and only if really didn't change anything. This statement, this S statement, and this biconditional where one is a tautology, didn't affect the truth values. These are logically equivalent, and we'll talk about that in a little more detail later on. But we finished up. We determined the truth table of this statement here. So we know exactly when this statement is true or false. It depends on the truth values of P and Q. So we are finished. The contrapositive of a statement, this is an interesting one. So the contrapositive, let me write down an example. Let's do that cat-mammal example. So if, let's say C is a cat, then C is a mammal. Well, the contrapositive says, well, you flip the Q and the P, the if and the then part, and you reverse the truth values. So the contrapositive well, it's going to be if, so we need to put the negation of Q as the if part. So it's going to be if C is not a mammal, since the then part is Q here. C is a mammal is the then part. So the negation of that is C is not a mammal. Then C, well, we'll negate the if part of the original statement. C is not a cat. So that's the contrapositive. That's how it works. Here is our P. Here is our Q. So the contrapositive, this is the negation of Q, and this is the negation of P. So it's not Q implies not P. Let's look at the truth table for this, and you'll notice something really cool. Let me give myself a little bit of room. So we need the negations, so let's just write them down so we can look at them. So not P and not Q. We also need P implies Q, and we need not Q implies, let me make that not a little bit better, not P. There we go. Okay. Again, let's write all the possible values for our statements, all the possible truth values. There we go. And the negation of P, not P, well, that's just going to flip the truth values of P. And the negation of Q is just going to flip the truth values of Q. Okay. So we know P implies Q. That one's easy. That's true, false, true, true. Remember, this is only false exactly when the if part is true and the then part is false, which is in this situation here. Not Q implies not P. Well, let's look at this. So, remember, this is going to be false exactly when the if part is true and the then part is false. So, here we have false, false. So, if the if part is false, so we know that this is going to be vacuously true. Here we have the if part is true, the then part is false. That's the situation where a conditional statement is false. Here we have the if part being false, and here we have the if part being false. So in both of these scenarios, we know that the conditional is true. And what we notice here, look at this. The truth values for P implies Q and not Q implies not P are the same in each situation. We know that P implies Q is only false when P is true and Q is false. We know that not Q implies not P is false exactly when P is true, and Q is false. These guys, because they have the exact same truth tables, these are logically equivalent. They mean the same thing. They're expressed differently, but they logically mean the same thing. Maybe pause the video now and try example 2.7 here. We have a conditional statement here. If a quadrilateral has 4 equal angles, then it is a square. So write out the contrapositive of that and determine if it's always true. See if you can find a situation where it's not. So if you can, that's called a counterexample. So pause the video now and try that. Okay, now that we're back, let's write out the contrapositive. So the contrapositive, remember, we're going to negate the then part and put it first. So we have if a quadrilateral, since that's our domain, if a quadrilateral is not a square, here's Q. So this is the negation of Q. And the reason I put quadrilateral in there, because it's just telling you what our domain is, what type of object we care about. So if a quadrilateral is not a square, then, well, the if part here is it has 4 equal angles. So here's our P, here's our Q, here's our not Q. So our not P is going to be, then it, oh, let me do this in black. It does not have 4 equal angles. All right. So the truth values of these statements are going to be logically the same. When one is true, the other is going to be true because these are logically equivalent. But there is a situation where we can find something that has 4 equal angles, but is not a square. And a counterexample to this is, of course, a rectangle. So rectangles have 4 equal angles, 90 degrees, but it's not a square. And that's this situation here, where the if part is true and the then part is false. So it's a quadrilateral that has 4 equal angles, so the if part is true, but it is not a square, so the then part is false. So we found a counterexample to this if-then statement. It's not always true. And if we look at the contrapositive, well, this is not a square, so the if part of our contrapositive is true, but the then part is false. The then part here says it does not have 4 equal angles, but it does have 4 equal angles. So we're in this situation where not Q is true, but not P is false. And again, that is the same thing. So these are logically equivalent. And this particular if-then statement has a counterexample. Again, we're going to explore counterexamples quite a bit more in the future.